The question says consider the following complex ions PQRs. Okay, three complexes given here. First complex, second complex, and third complex. Okay, it says the correct order of the complex ions according to their spin only magnetic moment values. Okay, always keep in mind spin only magnetic moment values depend on the number of unpaired electrons. Higher the number of unpaired electrons, higher is the spin only magnetic moment values. Okay, means this question is related to magnetic properties. Okay, any question related to magnetic properties, hybridization or geometry, always use valence bond theory. Okay, it is easy to use. The steps which we follow to apply valence bond theory, first step is what? We have to calculate oxidation number of central metal atom. Then we have to write electronic configuration of central metal ion. Then we write orbital notation. Okay, while writing orbital notation, you need to consider the effect of ligand. Whether we have a strong field ligand or weak field ligand. A strong field ligand will cause pairing of electron. Weak field ligand will cause no pairing of electron. We follow Hund's rule in case of weak field ligand. Okay. Now we go for the first complex. We have a Fe, and this is what? F6, and overall charge is what? -3 is there. Follow the first step. Calculate the oxidation numbers. So overall charge -3 is there. We have Fe plus 6 multiplied by each halogen is what? -1. Fe minus 6 is equal to -3. Fe is equal to -3 plus 6 is equal to +3. Fe is present. Iron is present in +3 oxidation numbers. Okay. So we got central metal ion Fe3 plus. For this we have to write electronic configuration. For iron we have atomic number 26. Outermost electronic configuration will be 3d6 4s2 is there. Now we have to write for central metal ion Fe3 plus is there. Okay, in this complex iron is present in +3 oxidation number, means it is losing 3 electrons, 2 electrons from here, 1 electron from here, then we get 3d5 is there. Okay, now we can write third step, orbital notation. Okay, we have to write the orbital notation for this central metal ion. Pay attention very carefully. So we have Fe3 plus is there. For this we write orbital notation. First we have d orbital. In d orbital how many boxes are there? 5 boxes. It is 3d5. 4s is completely vacant. Then we have 4p orbital. It is also completely vacant. Okay, while filling the electrons, we need to consider the effect of ligand. Okay, effect of ligand. What kind of ligand is there? In this complex, you can see ligand is what? Halogen. Halogens are considered as a weak field ligand. Means if weak field ligand is there is no pairing of electron. We follow Hund's rule. Okay. So first of all, we have to fill these spins, these electrons singly, and then we can double. Okay. So first is spin, second is spin, third is spin, fourth is spin, and this is the fifth spin is there. Okay, all the 5 electrons are filled. You can see it has a maximum number of unpaired electrons. How many unpaired electrons? 5 unpaired electrons. We got 5 unpaired electrons for this first complex. Iron has 5 unpaired electrons. Similar method we can follow to calculate number of unpaired electrons for vanadium and then for iron also. Okay, now move on. Then we have the complex vanadium H2O whole 6 is there and +2 is there. We follow the same step. Now pay attention carefully. We have the complex is we have vanadium. Okay, and then it is H2O whole 6 is there. All charge is what? +2 is there. Okay, is equal to +2 vanadium and plus how many water molecules? 6. Each water molecule is a neutral ligand, then it will have 0 charge. So vanadium is present in +2 oxidation numbers. Okay, so here we have vanadium present in +2 oxidation number. Now we write electronic configuration for the central metal ion. From here we are getting vanadium having +2 oxidation number. For this central metal ion we write electronic configuration. Vanadium atomic number is 23. We write electronic configuration, outermost electronic configuration 3d3, and it is 4s2 is there. Then we have vanadium +2 is there, means it is losing how many electrons? 2 electrons lost. Then it is going to be 3d3. Okay, then we go for the orbital notation. Okay, so we have vanadium 2 plus is there, and in this case d orbital how many boxes? 5 boxes. 3d3, 4s orbital, then 4p orbital are there, vacant orbital. Now in case of this complex, consider the effect of ligand before filling these electrons. Water molecule is there, and water molecule is a neutral ligand and it is a weak field ligand. Means no pairing of electron. So we follow the Horn's rule. Singly filled, second spin, and this is the third spin. So it is going to have how many unpaired electrons? You can see it is having 3 unpaired electrons. We got the answer for this complex. What is the unpaired electrons we got? That is 3. So we mention it is 3 is there. We have 3. Okay, in the last complex we have, we can calculate for that one also. This is what FeH2 whole 6 and plus 2 is there. Pay attention carefully. We follow the same method. We have Fe and it is H2O whole 6 is there, and but in this case it is having plus 2 charge. Okay, we have oral charge plus 2. Fe is there plus 6 water molecule. Each water molecule has 0 charge. So Fe is present in plus 2 oxidation numbers. Okay, from here we got Fe having plus 2 oxidation numbers. For this we have to write a electronic configuration. Fe atomic number 26, outermost electronic configuration 3d6 4. H2 is there. We have to write for Fe2 plus losing 2 electron lost. It is going to be 3d6 is there. Okay, very interesting. Now we go for the orbital notation. Okay, so we have orbital notation. This is what Fe2 plus is there. D orbital, how many boxes? 4 3d6, then 4s is there, and then it is going to be 4p is there. Very interesting. Now again we can see water molecule is there in the complex. Water molecule, it is a weak field again, means no pairing of electron. Follow Hund's rule. Singly filled, first, second, third, fourth, and it is fifth, and it is going to be double now. Okay, now it has how many unpaired electrons? 4 unpaired electrons. 1 2 3 4. 4 unpaired electrons are there. Okay, so now I go back to the question. Pay attention carefully. We have in the last complex, iron is present in 4. Iron is present. Yeah, iron is having 4 unpaired electrons. Now we can arrange. First complex P having maximum number of unpaired electrons 5. Then R complex is having 4 unpaired electrons, and then Q complex has a minimum number of unpaired electrons 3. So as the n value, number of unpaired electrons decreases, spin only magnetic moment value also decreases. Okay, so maximum will be for the P complex, then we have R, and then in the last it will be Q will be there. Okay, any such order given here, you can see we have option A is correct. Option A. Okay, if you flip it, so you will get the same orders. Okay, so P is maximum and Q is minimum. Very interesting question. If you like this video, please share and subscribe to the channel.